One of the most important properties of the MRAM is its incredible immunity to soft errors, particularly when compared to SRAM-based devices, with the benefit to the user being superior reliability. Let's take a look at the underlying technologies of both devices to learn more. SRAMs use a latch circuit that's sensitive to changes in voltage to store data. When hit by alpha particles and cosmic rays, this voltage level can be disturbed such that it can cause the SRAM memory cell to change state. That is, a logic 1 can turn into a logic 0 or vice versa. This, of course, means that the data becomes corrupted. MRAMs, on the other hand, use tiny magnetized elements to store data. When hit by alpha particles or cosmic rays, these magnetized elements are completely unaffected and will safely retain the data for a minimum of 20 years. Now here's where the story gets interesting. As the memory density increases, the size of the individual memory cells decrease. As SRAM memory cells get smaller, the voltage level present in each cell gets smaller as well, and therefore the likelihood of an alpha particle or cosmic ray corrupting the contents of the memory cell is even greater. Turning to the MRAM, as its memory cells decrease in size, they continue to be immune to alpha particles and cosmic rays, since the underlying storage mechanism is magnetic, not an electric voltage, and the end result is the same: absolutely no loss of data. Let's take a look at the failure rates of SRAMs as a function of their density. Because their memory cells are fairly large and their voltage level is also large, a 256 kbit SRAM has manageable failures when exposed to alpha particles and cosmic rays in most applications. At the 1 megabit density, the negative effects are more pronounced, around 100 fits, and at the 4 megabit density, a failure rate of 1,000 fits is encountered, certainly a major problem for many applications. At 16 megabits, the soft error problem becomes almost unbearable. Band-aid solutions using error detection and correction are frequently attempted, often at great expense and marginal effectiveness. Bottom line, as the physical size of SRAM memory cells continue to shrink, their exposure to soft errors will continue to get worse. We should point out that any type of memory that incorporates SRAMs are also victims of soft errors. This includes battery-backed SRAMs as well as non-volatile SRAMs, also known as NVSRAMs. And if the application uses one of the esoteric pseudo-SRAMs that actually use an embedded DRAM memory within its memory cell, the soft error problem reaches apocalyptic proportions due to the incredibly small charge stored in the DRAM's capacitor. What's more, other non-volatile memories such as flash and FRAM also fall prey to alpha particles and cosmic rays. One last note: neutrons are yet another source of soft errors. While not as prevalent as alpha particles and cosmic rays, they do appear and can affect semiconductor memories, including the MRAM. The good news is that the failure rate of the MRAM caused by neutrons is less than 0.1 fit, compared with thousands of fits with SRAMs. In summary, the MRAM is the undisputed leader when it comes to immunity to soft errors.